Good morning, everyone. Already, third minute is going on and people are still joining. That's not good. Anyway, so I'll begin. So last time we were talking about the microcanonical ensemble, right? And the conditions were as per dictated by the Lively's theorem. So of course, my density function, the density function was constant. In that scenario, I told you that the ensemble under consideration we termed as the microcanonical ensemble, in fact, right? So let me briefly say those things. Let me choose maybe. Okay, so yeah, in microcanonical ensemble, we saw that the macro state of my system is basically defined like this. This is how we define our macro state, right? NVE. So they were fixed. In fact, for a more realistic situation, my number of particles were fixed. The volume they occupy, that is also fixed, and energy is also fixed. Although, as I said, for a more realistic condition, the energy is basically fixed between this interval E plus minus delta. And then what we did was we basically went to the phase space where each of the Qi, Pi were mapped to microstate in phase space, and basically we calculated the volume in phase space, allowed volume, as constrained by this V and this energy interval E plus minus delta E, and then we computed the volume in phase space. Then we looked into that how much the minimum volume a microstate can occupy in phase space. That we computed, if you remember last time also, that that minimum volume, that omega naught, was approximately h cube kind of thing if my particle is one, right? So if I calculate the total volume occupied by my ensemble in phase space omega, then just dividing this by the unit volume, I would say I can calculate this number tau. And we saw this last time for microcanonical ensemble, right? And this thing, as I discussed last time also, so if you have your quantum state in phase space, I would say, then the delta q delta p kind of thing, it has of the order of this h bar. This is with basically the Heisenberg uncertainty principle, right? So if you attach 3 degrees of freedom with the q and p, then the this correspondence is bit understandable, that why it is h cube in phase space, right? So this is how your phase spaces somehow have a correspondence or analogy with the uh, quantum states of a system, right? Although we'll talk about this more when we'll working in quantum stat mech. So now at that point, as I just pointed out, that the idea was we compute this, the number of microstates for a given macro state, then we just derive the full thermodynamics. That's what we were talking about, right? Now, but we know that if we are having a physical system, right, and doing such calculation or computing the this number is not that easy, basically, right? It's not that straightforward as in case of, I would say, the ideal gas, the case we considered, or if you talk about the harmonic oscillator problem, which I left for you people to just give it a read and then see if you can do that. Or it's a quite straightforward calculation, a couple of pages, as I mentioned in last lecture also, right? So for those cases, this is considering your system from in a micro canonical ensemble is like good enough. But if you go to a more general kind of situation, maybe, right, then these calculations are actually really challenging, right? Computing this number tau, or the number of microstates accessible to the system, is not that easy, because for a realistic system, actually your energy is not something we are concerned about most of the time. It is even the exact value to find or to control it, so that to keep it in this interval, it's not that easy, right? Instead, a convenient parameter would be the temperature of the system, right? It can be measured easily, right? As well as you can uh, just give me one sec, just a minute, please. Okay, sorry for the disturbance. Okay, so what I was saying, yeah, so that instead of this energy, we can go for the temperature of the system, right? Because temperature is something which you can measure readily, and you can have a control over it very precisely. We have instruments to control the temperature. A very uh, quick example could be like an incubator in your lab, or maybe refrigerator could be one thing, right? So controlling temperature is more feasible in a realistic situation. So instead, so if we want to tackle a system where we are not controlling the energy or not limiting the energy window, but instead we are talking about the temperature, so we don't need to consider the ensemble where my energy is like fixed or is varying between window. Now we should be concerned about something where temperature is fixed kind of thing, right? So such a scenario doesn't come under this micro canonical ensemble, but the ensemble we will be dealing with is the canonical ensemble, and over there the macro state would not be specified by nve. So instead of this e, so we'll be talking about temperature now, temperature of the system, right? So this is going to be a switch. This is what alternative way would be. I hope you can appreciate this, that why we're switching from energy to temperature regime, just to get into a more realistic situation. Okay, so yeah, this is as I said. So instead of energy, we'll talk about in terms of temperature. Now this control, how we can have control with temperature. Basically, this I mean to say is that we can think of that like our system is in contact with a heat reservoir. Generally, you call a heat bath kind of thing, right? And heat bath, ideally, it has a infinite heat capacity. It means if you give it some energy or take energy from it, the temperature doesn't change actually. Okay, so that's the meaning of infinite heat capacity, although it's not a very realistic, but ideally it is achievable under certain approximations, right? And the heat bath has a fixed temperature T, so this T is not going to change over time, right? And we can, what we can do is we can keep our system in this heat reservoir or heat bath, and because the capacity of this heat bath or heat reservoir is so large that even if my system is exchanging energy with the heat reservoir, the temperature of the system as well as the heat reservoir is not going to change. So this way we can control this temperature T of my system, right? So yeah, this I already told you. Basically, I'm just making these note for your references, but things I'm talking maybe a bit in advance also, right? So we can go for those formal PPTs also, but I don't like that. I like writing things down, and these are basically in very much correspondence with your textbook, because I don't want to deviate much with respect to that. Okay, so yeah, this what I said. Now, or other way around, you can also think of in this situation that your heat reservoir, it is made up of large number of systems which are basically copies of your system under consideration. All are similar way, are the mental copy of each other, but all are at same temperature. But they can exchange energy now. Okay, and ideally this ensemble with such conditions are called basically canonical ensemble, and as such there is no limit on energy indeed, right? So energy can have zero value and it can go up to as large as required, but you will see for a realistic situation our energy would have some value, but this is in general it's a variable kind of thing. And now my macro state is no more dictated by NVE, but I will replace my energy by temperature, which is more controllable, you can say thermodynamical parameter, and we will control that with the help of this heat reservoir. There can be, as I just explained, there can be two situations: either you put your system into a large heat reservoir, or you just build your reservoir out of large number of mental copies of your system. This way you are going to make a ensemble basically, right? And such an ensemble for which every mental copy has same temperature, but energy can have slight variations. Such ensemble is called basically canonical ensemble, right? So now I'm going to define one parameter, the this parameter, the probability PR. Now, what does PR means? Let me explain and be careful, right? These are the definition. If you just skip this thing or you don't understand these things, then like you are going to face issues, because there are many things we are assuming or we are just having conditions on our, you can say, derivations. Assumptions are there. So if you don't listen to them carefully, you are going to lose it. Okay, because then things will get confusing as I will proceed further. So PR basically represent these ERs are my energy eigenvalues of my system. Do remember this. So it can be E0, E1, E2, and so on. I don't know up to how much, how many limits. For example, they can be different energy eigenvalues of a harmonic oscillator, just for example. Okay, or they can be continuous also in principle. Okay, they need not to be discrete always. So then my summations in this derivation, they will all change to integration. So this way trick we all know, but just for the discussion purpose, we are treating them to be discrete. Okay, so if I observe my system over at a given time t, it can be in any one of these large number of states, energy eigenstates, right? And these basically energy eigenstate, whatever the energy er basically dictates that what my microstate accessible to this. These are basically different microstates accessible to the system, right? Because I now made my energy a variable thing, so this can vary. Although there will be some constraint on these things also, but we'll see. But even being different energies, the temperature is going to remain same, right? That's how we build this thing is. So P probability, PR probability is the probability of system if at a given instant T my system is in rth micro state. That's this probability. Okay, so how we can go about it, or how we can calculate this probability? There are two ways, as I just mentioned above. Either you can think of in this situation or this scenario that your system is in equilibrium with a heat reservoir, and then you just study the exchange or just study the statistics that how your system is exchanging energy with the reservoir, and just come up with the thermodynamics of the system. That could be one scenario. Another scenario is something like this, that as I just said above, that consider that your system is a part of a large number of ensemble elements which makes full ensemble, the canonical ensemble. and your system is one member, and then it is exchanging energy with all other members, and but everyone is at a constant temperature T. So that is you can say ensemble consideration. But even if you see the thermodynamics derived from this consideration or this consideration, under limiting case they both will agree with each other. Okay, that should happen ideally, right? It doesn't matter which path you take to build your theory, but they should agree with each other independent of the path, right? Because they are representing the same physical system, although considerations are different. So until now, if you want to ask any question, that why so, what are these, why we're doing this, if you have any question you can tell me now. Otherwise I'll just start considering this scenario. So I'll start considering this. Maybe I'll try to finish this part today, and maybe my system in a canonical ensemble I'll begin with maybe some initial arguments, and we'll continue this in next lecture. So if you have any question you can type in, and I'll see, otherwise I'll move ahead. So I don't see any question coming. Okay, so let's move ahead then. So now my system, it's in equilibrium with the heat reservoir, because initially they may be at some different temperature, that my system is at temperature T and then my heat reservoir is at temperature T dash. But when I'll put my system into this thermal bath, thermal equilibrium is going to attain. That's what we learned. And then we defined one parameter, if you remember, the beta parameter, which was curly log omega by curly E dash, where this E dash takes the value equilibrium value. So this was how we defined this beta parameter, that when my two system comes into thermal equilibrium, and then they are going to attain equilibrium state only if their respective betas are same. This definition we are going to use here also. And if you remember, this was nothing, thermodynamically we proved that this is nothing but 1 by kt, where T is the equilibrium temperature, right? So but here in this situation I'm already considering that my system is in equilibrium with the heat reservoir, so it means they both have temperature T in the beginning. Okay, so because my macro state is defined with this nvt, so T has to be a fixed parameter this time, I can't vary T. Okay, so similar situations are there. N is the total number of particle in the system. V is the volume occupied by the system. And but now this consideration is not. We are going to jump into the phase space, for example. Okay, that phase has passed. So we are okay. So my system, I'm symbolizing my system by symbol A, and the reservoir by A prime. Mind it. Okay, and ER, if you can read this. So ER is the energy being possessed by system, and er prime is the energy possessed by the reservoir, although they can exchange these energies, right? Because they are in thermal contact, temperature has to remain constant, but they can interchange the energy. That's a variable kind of thing. Okay, and this was different when we were discussing the micro canonical ensemble. Okay, at that point my energy was fixed, either it was had a precise value, or it was varying between a very fine narrow window of E plus minus delta E by delta by 2, where delta is almost negligible as compared to E. So window was very fine. Okay, yeah, temperature T, and yes, the total energy is going to be constant. The energy possessed by the system and heat reservoir, they are going to be sum is going to be constant, but they are interconvertible. Okay, but as I said, there is one, this is very important, you can say argument, that my reservoir has a large heat capacity. It means my system, my reservoir, heat reservoir, it is very large as compared to system. So basically the magnitude of this er prime is very very large as compared to er. So most of the Uh, I think we lost the network in between. Now, am I audible? Can somebody comment? I think I should be. Yeah, I can see I'm online now. Okay. Okay, thank you for letting me know. Let's resume. So I'll briefly say this again. Maybe you might have missed this due to this network issue, but that's okay. So I'll quickly say it again. So basically, I was discussing that my system, which is being symbolized by this symbol A, is in thermal contact with a heat reservoir, which is very large in its volume and as well as energy. It looks that we are facing some connectivity issues, but that's okay. I think Monday onward, this section is going to have classes physically, so that would be best actually. Okay, so let's resume. So, as I already said, that this energy possessed by reservoir is very much higher than energy possessed by the system, right? So means this ER by E0 is very less than as compared to 1, and this you can very easily follow just putting value of ER from equation number 1. Now, as this ER prime is very large as compared to ER, and there can be a large number of states in which my reservoir can be. Please mind it, I'm talking about now the states accessible to the reservoir, not the system. Okay, so that I'm representing by this symbol omega prime ER prime. I think you can understand why it's a function of ER prime, because different energy eigenvalues for the reservoir, the number of states it can be in the heat reservoir depends upon these energy eigenvalues, right? Similarly, I'm putting one prime here. This prime basically means to say that what's the structure or internal structure of the reservoir is. Although this detail is not going to matter in our discussion, but there is a deeper meaning of putting this prime. Okay, so it means that what type of a heat reservoir or is there, or what are the discrete or maybe continuous energy values it can take. So that is basically mentioned here with this prime, although we can ignore this, but that's okay, right? So if this omega dash er dash is a large number, then the probability of the reservoir to be in this particular energy will also be high, right? So basically this is nothing but it is something called your thermodynamical probability of your system also. So larger the number this is, so how you can think of that how it will be larger actually. So this er is a variable kind of thing. Okay, mind it, this er is variable because your reservoir and system can exchange the energies. So it means that my system can have different energy and my reservoir can have different energy. This keeps on changing, although temperature will remain same. But and of course if this er is varying, now this number of states accessible to the reservoir, it will also vary. Now my argument is, largest the number this will be, this these number of states, more the probability of the reservoir into that system. So if the reservoir is going to be in a particular state with energy ER, then the probability of A is also going to be high in state with energy ER without prime. Okay, so this is very strong argument basically. So basically what it is saying, that probability of system to be in energy eigenvalue with index R is basically proportional to this number. See how strange this thing. These are the states of the reservoir. Larger the states of the reservoir, then probability of reservoir in that particular state ER dash will be higher, and correspondingly the probability of system to be in some energy eigenvalue ER will be higher. That's simple. That's why probability of system is proportional to the number of the states accessible to the reservoir. Hope you got this. Okay, we can put this into number also. Yeah, this is what I wrote. So this probability is proportional to the number of states accessible to the reservoir, and this is the probability for the system to be in eigenstate ER at a certain instant of time t. Okay, and this is nothing but you just change your ER prime as E0 minus ER, because ER plus ER prime, it was total you can say energy of the composite system, where A plus A prime makes my composite system A0. We saw this something earlier also, when we defined these various parameters, beta, eta, zeta kind of thing, right? Various kind of equilibriums we saw in chapter 1. Okay, so now what we can do, we can just to have the behavior or deeper understanding of this probability, that how it is going to vary with the in fact this ER, right? So I can expand this number, or this condition is exactly same as I'm saying like this, right? So we are basically expanding this function. If you can just a minute, this expansion, these are bit mathematical steps. You may find it bit maybe confusing if you don't follow that how you like Taylor expand things. So I'm expanding this now. There is one more you can say step. Instead of expanding this function, this one or this one, because both mean same, I'm not expanding this, I'm basically expanding their log just to converge this series, because you know these numbers are very large. So I'm just taking their logarithm just to make the series converging. Okay, so this function is equals to, because I'm expanding as I said at ER prime equals to E0, because if you do this from equation 1, which is here, if I'm making my ER prime equals to E0, it means I'm expanding around ER equals to 0, right? So where my system doesn't have any energy, I'm expanding this around that point. So this will be equals to log omega prime E0 plus differential of this function with respect to E prime. I can't put R because ER has certain maximum value. So I'm just sticking that how it is varying with energy, and evaluate this differential at E prime equals to E0, because that's what we are doing, right? And of course multiply by this interval ER prime minus E0. And if you see that this first number is a constant thing, because these are the number of states my reservoir can have when full of the energy was possessed by the reservoir. Okay, so and this is constant because E0 is not a variable thing. And although I said that this is a homework, you check, but I already gave the answer that this number is going to be a constant thing. Okay, and this, as I just told in the beginning, here at the top is nothing but the beta function of my system, right? So I just replace this number by beta dash, because these are differentials with primes. Okay, prime means they are for the heat reservoir, not the system. And this E R prime minus E0, it is nothing but uh, negative of the system energy. Now there, mind it. Okay, so I just replace this here, and beta prime. And by the way, beta prime which is nothing but 1 upon kt prime kind of thing, it will be equals to basically 1 by kt, right? Because my system is in equilibrium with the heat reservoir. So we can in fact replace this beta prime with beta also. Okay, So if I now take the anti-log of on both side of this equation number 4, you will see that omega prime er prime is approximately is exponential of this constant multiplied by exponential of minus beta prime er, right? Because they are summed over, so exponential can be multiplied like this because they are not operator, so it will follow this rule. And as I said, at equilibrium, this is going to follow this situation. And so what I mean to say is that this number of states accessible to the reservoir having energy er prime is proportional to e raised to power minus beta er, right? So this is the kind of you can say end result we saw by expanding this function around er equals to 0. So now if you, it means because my probability was proportional to this guy, so it means my probability is proportional to this number now. Okay, so we can normalize this number, because suppose we can, I can, how to normalize basically, so I can calculate my probability in state 1, that will be proportional to, actually in fact, yeah, so e raised to power minus beta e1, because that's what it is saying, right? Minus beta er. So similarly, I can calculate probability in state 2. So then that would be e raised to power minus beta e2. So this way I can continue this. And if I sum over all the probability, they must sum to 1, right? So if I convert this proportionality into equality, there must come some constant of proportionality. I don't know. Let me maybe put capital K, right? So that K we can evaluate because this probability are going to sum to 1. So that K would basically give me 1 by summation e raised to power minus beta er. So that's called the normalization. So basically, if I want to convert this proportionality into equality, so I have to divide this number by this summation, because they are going to sum to 1, right? So this is how I can get the result for this normalization after normalization. And this is quite interesting, that this helps me to find the probability of my system with energy er given by this thing e raised to power minus beta er by sum over all the states. You might have heard about something like this in the denominator is something related to your partition function of the system. We'll talk about this more, and of course this summation is running over all the states accessible to the system. Okay, any question till now if you want to ask? No questions? Okay, so let me say a few things now. I'll begin with, as I said, uh, this was the probability I calculated. In fact, if you remember, we begin with this argument that I can calculate this probability where I said, just let me go to my earlier slide. One page back here, that I am interested in this probability for my system A to be in energy eigenstate ER. I want to calculate this. So I told you that we can calculate this in two different ways. So one I already did when my system is in equilibrium with the heat reservoir at temperature T. But we can also do this by assuming that my system is a part of a big canonical ensemble, and considering their statistic, we can again calculate this probability. And this is going to be a bit challenging, but I'll just begin with, and maybe we'll resume this next time. Okay. So what's the idea now? So now I'm considering, of course, now my system is in a canonical ensemble. Mind each term, okay? That what you must be aware that what we are doing, because getting lost or getting confused is very easy in this you can say article, right? So because there are a lot many parameters are going on. So I'm considering my ensemble. Mind it, the number of particle with which my macro state was defined was something like, so these were the number of particles in the system. This is something else. It is the number of ensembles now in canonical ensemble. And these are just mental copies of each other. These are all identical system. All are characterized by same macro state. Okay. And the total energy which is available to all these systems, there's some actually I'm talking about, not this energy which we replace this energy with this temperature. I'm not talking about the energy of individual system. That is a variable thing now. Okay, I'm talking about the total energy of similar to this is something similar which we talked just before this, that my E0 of the composite system was equals to energy of my system A and energy of the reservoir E prime. But now I'm replacing this guy with this energy E, and now energies are distributed among all n identical mental copies, but their sum is going to be constant. I'll tell you what are the constraint on this ensemble actually, right? So this energy is something different, but these are constant, mind it. Okay. ER is the these symbols are basically representing the system's energy eigenvalues. Okay, the system, each of these n systems can be in any one of the eigenstate of this these kind of thing. So it's like you can put it like this also. So they may not be equally spaced, they may not be continuous or discrete also. Okay, so E0, so out of these n identical systems, maybe two systems can be in energy eigenstate E1, right? So maybe out of them three can be in state suppose E4, and so on. They can have different energy values, no problem, because energy, and they can exchange energy. Even different systems in this ensemble, they can exchange energy. That's the whole idea of canonical ensemble. But the total is going to remain constant. This is not going to vary, right? And in fact, we can write these conditions very easily. If I sum over all the number of ensemble elements on various energy eigenvalues, this sum has to be equal to the total number of ensemble elements, right? And if, as I'm saying, if my two systems are, for example, here, maybe three systems are in energy eigenvalue E1, and maybe one in E4, and so on. So what's the total energy being contributed by this towards the total energy? So that will be E1 into N1. So that's the N1 number of systems are E1 and energy eigenstate out of these ERs, right? So similarly for second level, so that will be E2 number of N2 number of ensemble elements. They are in E2 energy states. This sum can go on, and this whole sum has to equal to this total energy of all the systems, right? Although this is not something physical, this E, because this is just a consideration we are looking at. So this has to be respected. All actually both these condition has to be respected all the times by this ensemble. Okay, and if I just divide the total energy available to n, if this is the total energy of all the ensembles, so average energy per ensemble I'm representing by this symbol U. Okay, so this is the average energy. So actually I will have energy fluctuations with respect to this energy. So my any ensemble can have any of these ERs. So how much this will fluctuate from this average energy, we'll see that also under energy fluctuation and even number fluctuation discussions, right? Okay, so what more I want to say is, yeah, I think I should continue with this next time, because I think we are, this connectivity issue wasted our almost 4 to 5 minutes, but that's okay. I think we'll resume from this point, and please do read about this, right? Because tomorrow again we have lecture. Do read. If you don't read, you are going to lose it for sure. Okay, thank you then. So you may leave if you don't have any question. You can ask questions also. Thank you.